Hi everyone, welcome to my YouTube channel. Today we will be discussing about the delta function potential. Let's say the potential is on the form Vx equals to minus alpha delta x, where delta x is the delta function, and the potential looks like this: an infinite well at the origin x equals to 0. The time independent Schrodinger equation reads minus h car square by 2m d2 psi by dx square minus alpha delta x psi equals to e psi. Now let us talk about bound state. We have already discussed about bound states and scattering state in very detail in the previous lecture. So if you haven't seen that, please see the lecture before you come to this lecture. So let's begin with bound state. We can see from the figure that potential is 0 for x less than 0 and as well as for x greater than 0, but there exists an infinite potential at the origin. So for x greater than 0, we can write the Schrodinger equation as d2x by dx square equals to minus 2mu by h car square psi, and I am writing this as k square psi, where k square is minus 2mu by h car square. Here the energy is negative, so k square is positive. K is a positive number or constant. So the solution of equation 3 is psi equals to a e to the power kx plus b e to the power minus kx. We know that psi equals to 0 for x equals to or x tends to plus minus infinity, but if we put minus infinity in this equation 4, the second term, this b e to the power minus kx term, blows up, and we cannot take that as a solution, so we put b equals to 0. So our solution becomes psi equals to a e to the power kx for x less than 0. For the region x greater than 0, the equation will be similar, but in this case we will put x equals to infinity, because for x greater than 0 the range of x is 0 to infinity. So for x tends to infinity, the first term, the term with the constant c, blows up, so we put c equals to 0 and our solution becomes psi equals to d to the power minus kx. And we know that psi is continuous at the boundary, so from equation 6 and 5 we can get a equals to d. So psi x, or our solution becomes a to the power kx for x less than equals to 0 and a to the power minus kx for x greater than is equals to 0, and the solution looks like this. As the potential is infinite, so d psi by dx will not be continuous. We know that if potential is finite, d psi by dx is always continuous, but that is not true for infinite potential. In that case, we have to integrate Schrodinger equation from minus epsilon to epsilon, including the origin, that is just before the origin and just after the origin, and take the limit epsilon tends to 0. So after integrating the Schrodinger equation, we get minus h car square by 2m d2 psi by dx square dx minus epsilon to epsilon plus vx psi x dx minus epsilon to epsilon equals to e minus epsilon to epsilon psi x dx. So if we put the limit epsilon tends to 0, this is not infinity, this is 0. then the integral on the RHS, this part, will be 0, because if epsilon tends to 0, so psi x almost become constant and came out of integration, and the small interval will be 0, so the total integral is 0. So the equation becomes d psi by dx. D psi by dx means the integration of d2 psi by dx square is just d psi by dx, and the limit is minus epsilon to epsilon equals to 2m by h cat square vx psi dx. We are just putting the limit, and we are putting Vx equals to minus alpha delta x. So this is delta d psi by dx, the change in d psi by dx across the boundary, and minus alpha comes out of the integration, so 2m alpha by h cat square with a minus sign, and we are left with delta x high x dx. And we know that this is a very peculiar, or what we can say, a important property of delta function, that it picks the value of the function at the point where the peak of the delta function exists. In this case, the peak of the delta function is at x equals to 0, so it will pick psi 0 out of this integration. So we have done the same thing here, psi 0. So from equation 7, what is equation 7? This is equation 7, the value of psi. So from equation 7 we will get a k to the power kx for x less than equals to 0, and minus a k to the power minus kx for x greater than equals to 0. So d psi by dx at 0 plus is minus a k, and d psi by dx at 0 minus is a k. 0 plus 0 minus are just points just after the origin and just before the origin. So delta d psi by dx, we know that delta d psi by dx is just d psi by dx at 0 plus and minus d psi by dx as 0 minus. So if we put that in this equation, so we get minus 2ak. From equation 9, this is equation 9, from equation 9 we get minus 2ak equals to minus 2m alpha by h cat square into a, because we know that psi 0 equals to a. Here in equation 9 we have to put the value of psi 0. So k equals to, after simplifying we get k equals to m alpha by h cat square. We know that k square is minus 2m e by h cat square. We have already chosen this in previous equation. Let's see where we have considered this. This is here we have considered this. K square is minus 2me by h cat square. So let's just put that in this equation, and from here we can see that E equals to minus h cat square k square by 2m. And now put the value of k square from equation 10. So we get minus m alpha square by 2h cat square. Here we can see that only one energy is possible, so we get only one bound state. Now let's normalize psi. As we can see from the graph that psi is a even function, so we can integrate minus infinity to infinity, or we can integrate 0 to infinity and multiply it with 2. And we know that psi x is a to the power minus kx for x greater than 0. We have just put that value here in this equation, and there is a standard gamma function integral. You must remember this formula, it will be very helpful for many integrations in quantum mechanics. The formula is x to the power m e to the power minus alpha x to the power n dx. Integrating it over 0 to infinity, we get 1 by n gamma of m plus 1 by n by alpha to the power m plus 1 by n. We are just using this formula here. So here we can say that m is 0, the m is 0. So according to the formula, n is 1 and m equals to 0. So if you put those values accordingly, you will get gamma 1 by 2k. And we know that if we have to normalize this, so this has to be equal to 1. So a is root over k. We are just taking the positive real root, and we know that value of k is m alpha by h cut square. So just put that and we get root over m alpha by h cut. So psi equals to root over m alpha by h cut. This is the value of the constant, and then e to the power minus m alpha mod of x by h cut square, because the value of k is m alpha by h cut square, and we are taking the mod x because if x is greater than 0, then this gives minus m alpha x by h cut square, which is satisfying with our previous derivation. And if x is less than 0, and this gives m alpha x by h cut square with the positive sign. So then that also is obeying our previous observation or previous derivation, and energy is minus of m alpha square by 2 h cut square. So we are now done with the bound state. Now let's move towards the scattering state. Scattering state means the energy is greater than 0. So for x less than 0 and Vx is 0, we have our Schrodinger equation d2 psi by dx square equals to minus 2me by h cut square psi, or minus k square psi, where k square is 2me by h cut square. K is positive. Solution of equation 14. Sorry, I have just written off twice. Solution of equation 14. Psi equals to a to the power ikx plus b to the power minus ikx for x less than 0. Similarly, for x greater than 0, we have the similar conditions, and we get psi equals to c e to the power ikx plus d to the power minus ikx. We know that e to the power ikx represent a wave propagating to the right at t equals to 0 or towards the positive x direction, and e to the power minus ikx represent a wave propagating towards the negative x direction. But if in an experiment the particle is projected from left, we can take d equals to 0, because let me show you a picture. And if the particle is projected from left, it will bounce back from the potential barrier, and also it may transit from the barrier. But the equation d to the power minus ikx is useless for that case. So we are taking d equals to 0. So psi equals to c to the power ikx from equation 17, just putting d equals to 0. And we know that psi is continuous at the boundary. Applying that condition, we get a plus b equals to c. Now let's determine d psi by dx. For x less than 0, it is ika e to the power ikx minus ika b e to the power minus ikx, and for x greater than 0 it is ikc e to the power ikx. So d psi by dx at 0 plus is ikc, and at 0 minus it is ika minus b. So delta d psi by dx is ikc minus a plus b. So from equation 9, what is the equation 9? The equation 9 is delta d psi by dx equals to minus 2m alpha by h cut square into psi 0. So delta d psi by dx is ikc minus a plus b. We have just determined that. Just put that value here, and psi 0 is a plus b. Psi 0 is a plus b or c, you can put anything because those are same. And now just simplify this equation to get the value of c. So I am just transferring the value ik, or the constant ik, to the right hand side of the equation, and then taking a and b to the right hand side of equation, and just simplifying it. And here the value of beta is m alpha by h cat square k. I just used the constant beta to simplify the equation, and it looks neat and clean in this form. So from equation 19 and 22, 19 is this equation a plus b equals to c, and 22 is this equation c equals to this one. We can equate the ab part from both the equation. So a plus b equals to a 1 plus 2i beta minus b 1 minus 2i beta. So just rearranging a and b separately, we get b equals to I beta by 1 minus I beta into a. And from equation 19 is a plus b equals to c. So if we put the value of b in terms of a here and simplify it, we get value of c in terms of a. So the reflection coefficient, that is the relative probability that an incident particle will be reflected back, is r, which is given by b square by a square. And from equation 23 we can write b by a is I beta by 1 minus I beta. So after squaring them, we get beta square by 1 plus beta square. Similarly, the transmission coefficient T, or the probability of an incident particle to be transmitted, is c square by a square. After using the equation 24, c equals to 1 by 1 minus I beta into a, we get 1 by 1 plus beta square. The total probability must be 1. So let's check that. If we add r and t, we get 1. So that is confirming our theory. So we know that beta equals to m alpha by h cut square k. Now just square both sides, we get beta square is m square alpha square by h cut to the power 4 k square, and we know k square is 2me by h cut square, and just put that value in this equation, we get beta square equals to m alpha square by 2e h cut square. We know r equals to beta square by 1 plus beta square, and after putting beta square as m alpha square by 2e h cut square, we get this equation. And similarly, after putting beta square value in this equation, we get the transmission coefficient in terms of energy as 1 by 1 plus m alpha square by 2e h bar square. So from equation 28 we can easily see that higher the energy, the greater the probability of transmission, because if E is greater, then this term, this second term in the denominator will be very small. The denominator will be small, and we know that if the denominator is small, so the total value is greater or higher. We can also see that the solutions are not normalizable, but the general solution is a linear combination of these sinusoidal functions. The exponential kind of functions are known as sinusoidal functions, and the general solution is just a linear combination of them. They form a wave packet, and that wave packet represents the particles wave function, and that can be normalizable. Thank you so much for watching this video. Hope you enjoyed and learned something important or valuable. Please subscribe my channel and share it. See you in the next lecture.